Take it away.
Okay. Good afternoon, everyone. My name is Stefano. First of all, well done for making it all the way through all these amazing talks that you had today. Hopefully this is not going to be too long and tedious and no one is going to fall asleep. So this talk is about polymorphic and metamorphic attack. I thought that polymorphic was already too big of a word, so I didn't want to add metamorphic there as well. And how we can use behavioral defense and analysis to try and detect all these new attack patterns. There are going to be a lot of mythological creature names in there. So the reason why we have Cthulhu there is because at the end of this talk, I will release Cthulhu publicly on GitLab. So anyone can go there and clone it and take a look at it and play with it. So hopefully we're going to be able to invoke Cthulhu at the end of the presentation. Also, this presentation lacks memes, and a lot of them. That is the only meme I have in my whole presentation. And the reason for that, I'm sorry. The reason for that is that I have a lot of schemas, and those took the majority of the screen space I had. So I'm going to quickly go through all these points. So a bit of introduction of who I am, why am I doing this to the whole world, and then we're going to talk about a few of the terms that we're going to use through the research. Then we're going to talk about the scope. I have a proof of concept and a live demo, which probably will crash, but we'll try. We're going to discuss the results and then a few words about cybersecurity in general and the trends that I see in this world. So who am I? My name is Stefano. I used to study at the University of Glasgow. I graduated last year, and my passion is creating events for students around cybersecurity. So I organize that event, which is a cyber defense exercise. We have it every year at Glasgow Uni. And this event actually inspired me in doing this research as part of my degree, because as part of organizing the cyber defense exercise, we need to come up every year with vulnerable machines like you would have on VulnerHub. And then after 24 hours that the student tried to harden them, myself and a team of professionals from the industry actually try and do some pen testing on these machines. And when you know what the vulnerabilities are, all the majority of the red team work is very tedious and repetitive. You already know what you're about to crack. And so I found myself and the rest of my team repeating the same things over and over and over. We run and map, we see if the ports are open, we ping scan them, we do the same thing over and over and over. So I thought about myself, what about taking automation of all these tools, weaponizing a bunch of Metasploits and other bad tools that are out there, and see how successful that is. And that bears the question, why? Why do you do such thing? First of all, there are examples in the wild that polymorphism and metamorphism as mutations of the same virus or the same payload or the same exploits are happening in the world. If you think about Confrecker, which was one of the first worms, it would automatically expand. After that, we have Stuxnet, which had 40 days that was able to pass from system to system. After that, we had WannaCry. I think that everyone in this room know what WannaCry is. And again, we saw for the first time a virus that didn't need a user to double click on an email or download more ram.com. But if your machine was vulnerable and exposed on the internet, you were infected. And more recently, we had a few campaigns that actually targeted a few shops here in the UK that used domain generation algorithms. Which means that their command and control server wasn't only on one single IP address or one single domain. It would automatically generate and mutate the string in the code so it would maintain connection. So we kind of see how the trend in all this technology is going towards spontaneous mutation of the code. The code itself deciding to change, to try and make our life as security researchers way, way, way harder. So I wanted to, first of all, safeguard critical infrastructures. So when I did this research at university, I was focused on safety critical systems. So I had access to the clone of certain operating systems that were deployed in proximity of, you name it, your nuclear power plant, your power grids, and all these systems. So I was wondering if there was a way of securing the systems that are attached to very delicate infrastructures. Second of all, to track mutations, we have a huge effort in the community trying to track APTs and how bad people do bad things. And I think that if we put a huge effort into tracking the various mutation of all of these viruses, we're going to be able to pinpoint this infection much quicker. So if you think about WannaCry came out, infected a bunch of computers. Months later, we had not WannaCry, Petya, not Petya, all different versions of substantially the same thing. Definitely to combat what I like to call digital crime as a service. So the way I define digital crime as a service is, well, you have your Amazon, which is, like providing a service to you. And if you go on the dark web, you have this malicious actors trying to sell viruses. And it's not like it used to be in the 90s anymore, where you would get your random prorat that would work an afternoon on your friend's computer. Not that I've ever done that. And that was it. You have proper criminal organizations following software engineering practices. I'm talking, they have Scrum meetings, they have repositories, they have client support, they have video tutorials. They are organized. It's not just a sporadic, it's an exploit, it's a 0 day on the dark web, is point and shoot. Everyone that doesn't even understand viruses can just download it and execute it. And then command and control servers, which is what this POC heavily relies on, are still pretty much a thing. As we said it with domain generation algorithms, it's much easier to use the same command and control server and manage to spin it around. But if you think about it, and the general trend of computing science in general, we heavily relies on web APIs. We heavily rely on cloud as a service. So with all this in mind, it's normal that every computer in big corporations, even in nuclear power plants, needs to call out for their API, need to be accessible from remote. So all these dynamics allow command and control servers, which, if you think about it, it sounds like a bit of a stupid concept, having one single point of failure that all your viruses call back to. But are still pretty much a thing, because we need this external communication to actually make the things work. And lastly, because why not? If a fourth year grads could actually come up and build this, then why shouldn't we investigate these things? So let's talk about jargon. And the reason why I had to put up this definition is because whilst I was researching the paper, I came across various papers, and I was trying to find one definitive definition of code polymorphism and code metamorphism. And within the same semantic reports that I read, it gave 3 different definitions of polymorphism and 2 different definitions of metamorphism. So we're talking about the same paper written by the same person that gives you 3 different definitions of the same thing and 2 different definitions of the other. So just for the sake of this paper and this talk, we're going to define polymorphism as your code maintains the same logical context, but changes the semantic. So if you think about it, imagine having a for loop that repeats that you need an action to be repeated 4 times. You can have a for loop with an I counter that increments and does the thing 4 times, or you can have a while loop with some different variable that you check. So at the end of the day, the 2 pieces of code that you've written, they do the exact same thing, but they're written a different way. Why is this important when you talk about cybersecurity? It is because when you change the syntax and the semantics of certain commands, the signature and the strings in a certain file change. And when these small blocks of code change, if you have a low-level signature-based defense systems, this will not be triggered anymore. When we look at metamorphism is similar to that, but a bit different. So in this context, we want to end up doing the same thing, but we are going to change the logic on how we get there. So we still want to go from A to B, but we're not going to take one route. We're going to take another different route. So this changes a bigger chunk of the code. If you think about cybersecurity and what you normally do in an engagement, what you normally do is you look at a system and you need to choose an exploit, first of all. The exploit will try and breach in the system. So if you're trying to, for example, breach SMB, you have a lot of available exploits that allow you to breach SMB. So in this case, what we want to do is change the payload and the exploit and the different encoding and even the language in which we write this virus. So we're not only changing a for loop into a while loop, or vice versa, we're changing entire logic of the code. And as you can imagine, if even the previous method was successful enough into fooling certain low-level signature-based defense systems, this one is even more effective. So I had to set up a scope. As any good researchers know, I don't like to end up in prison, so I wanted to put some clear guidelines on what I was allowed and not allowed to do. First of all, I wanted to create a segregated environment in which I could test this. That need to be multi-platform, so not only Linux. So in my test case, I had Linux, I had Windows, I had OS X. It needs to be production-like and with a standard configuration, which means that I need to do a bit of research and knowing exactly which systems were deployed, which were the system that I was trying to protect to make the testing conditions as similar as possible to, as similar as possible to real life. And with a varying network topology, so not even just a flat one. I didn't want to just spin 20 VMs on the same subnet. I want to spin 3 on one subnet and then another 2, 3 subnets. I have different layers of communication to see how fast it would spread around. And finally, of course, you want to audit it. You want to save some data. So in this case, what I did, I just saved a pcap of the file to see how noisy it was on the network. The goal is to create 2 different agents, as I call them. One of them is the attacking one, and the other one is the defending one. So the attacking one, I called it Chimera, and the defending one, I call it Bellerophon, because we all do computing science, and we all like to give big and bad names to our programs, because why not? We create them, we can name them. So what you're going to see in this talk, and I'm going to talk first about this, is how I created Chimera, which is this polymorphic vector that completely changes, and how I created Bellerophon, which is a behavioral analysis system that looks at the behavior of all the machines and try to understand which ones are infected and where the infection is spreading. Cthulhu, which is the tool that I'm going to release after the talk today, which is also the one that I'm going to do a live demo of, is a primer for Chimera, which means it's not a point and shoot kind of tool. You cannot just clone it and point it to your friend's machine and think that it's going to do something. It's written entirely in Python. It's very modular. And you can recreate Chimera very easily with 40 minutes of work on Cthulhu, or you can create something worse or something better. The sky's your limit. So what I wanted to release to the public, for the public to go ahead and do, is create your own environment, create your own attack vector, and test it. And every single time test it, try and create a way of detecting it. As everything with computing science and cybersecurity in particular, be ethical. Don't do anything bad. Don't get arrested. And don't call me for that. The only reason why I'm releasing this tool is for research to go ahead and work. And finally, the flag at research when I was at university was just an MD5 signature that was hidden in these machines when the virus was breaking into it. To prove that I actually broke into it, I was basically just TCPing back this string and comparing it with the one that I had stored to confirm that I actually compromised it. So, as we talked before, I wanted to do a bit of research to make sure that the environments I was testing on was as similar as possible to the live version of these things. So I went to Shodan. Anyone here knows what Shodan is? Yeah. So I went to Shodan and I did a bit of research to try and see what were the most used environments in proximity of safety critical systems and PCI controllers, is not probably the best caller. But from up, we have like 4 or 5 Linux systems. Then you have Windows 7, Windows 8, Windows 6.1. You have a bunch of Windows servers, and then FreeBSD. OS X does not appear there. So apparently no one uses Apple computers in proximity of these things, or at least not publicly, not that Shodan knows of. And then I did the same thing about the services. So I wanted to deploy the same services as close as possible to the ones that were deployed in these machines. So again, OpenSSH, of course, you need to get into it. Apache for some odd reason. Then we had, a bit down in the list, we still have Samba, our favorite friend. And then we have Postfix, SMTP, and other things. So this is the very, very first initial iteration. We're talking 1.5 years ago, of the environment that I was testing this on. So you see, I had my host, which was a Kali Linux box, and inside of it, I had VirtualBox that was properly segregated in Sandbox, so no connection was going out. I had 4 machines that were protected, 4 machines that were not protected, and I would just release the virus in this environment and see if the protected machines would detect the virus before bad things would happen, and how fast how far I could go infecting the unprotected machines. So the very first edition of Chimera was fairly straightforward. So in the first bit that you find is just your common network scanner. Think a ping sweep or an ARP-A kind of command. This is where you land on a network and you try to understand which computers you can connect to. The second part is the target scanner, or actually, in all honesty, a port scanner. So what I would do is for each target that I found, I would just try and see which ports were open. Then I would generate a report, which is just a JSON file with all this data. I would encrypt it and send it over to my command and control server, which would then compile and send down a new version of itself that was, again, mutated. And then I would just execute it on the target machines. And this was a very straightforward, as you can see, kind of linear architecture of this first edition. It was just a proof of concept, and it did work. So just to give you a bit of context of what these 3 terminals are doing. So up here, in this part of the screen, you can see the report being generated. So as I said, it's a JSON file with IP addresses and a list of ports that are open. The second bit, this is the actual Chimera command and control server, which receives the message, decodes it, and then goes target by target, try to exploit it. And at this point, I was heavily relying on Metasploit. So I think that everyone that has used Metasploit knows exactly what is going on here. So I would automate the process of using Metasploit to actually hack into the targets. And it worked. So time for making it much, much worse and much more complicated. So it's probably easier to understand how this works in layers. So if you think about very good automation tools, for example, Metasploit or Empire and all these things do a lot of things for you. So when you just try to exploit a system, they will compile, they will choose the exploit, make the changes in the variables, compile it, make sure that the payload is compatible, send it over, start a listener, get the listener back, and they just make the whole magic work. If you want to write a highly polymorphic and highly adaptive virus, you need to dissect every single section out, because you need to have full control on every single step that happens within the virus creation and the attack creation method to be able to change it. So at the bottom layer, this is the target network. These are the compromised machines. So at the second layer, you have what happens in the local version of your virus, which would be kind of sort of the payload. Although in here, the payload is just a meterpreter shell, which is in charge of executing the commands and making sure that everything runs on the virus stage. Then you have the command and control server, which is where all the logic happens. So it would receive the communication and would decide what to do. And then lastly, you have Metasploit. As we said in this very, very early on version, I was heavily relying on Metasploit because I knew it and I knew how to work with it. And finally, you have Veil, which is a tool that allows you to do a bit of obfuscation. And finally, we have a server whose only purpose is to deliver all these different tools. It's fairly straightforward and similar to the first version in what it does, but it's a bit more distributed, which meant that at this point, I wasn't just writing a one-liner in Metasploit and just saying, go and hack. I would generate the payload myself. I would change it myself. I would generate the exploit myself and change it myself. I would create the listener. I would create a unique key for the transmission of the code and the encryption. And I would just do everything manually. Cthulhu, which is the tool that I'm going to be releasing, is a bit more open and very much more modular. Because the whole idea behind Cthulhu is that you are able to completely change a module. So, for example, the communication module in Cthulhu that Cthulhu comes with is just simple TCP sockets in Python, which anyone that understands how intrusion detection systems work is not going to fool anyone. But there are very valid tools out there that you can easily implement. So DNSCAT is one of them. So if you want to implement DNSCAT in it, you just need to go create a parser for DNSCAT, implement it, import it, and it's going to work out the box. Same thing with all the different stages. So it's more of a teaching tool because you can make it work once and then change just one single variable, see how it works, see how much is detected or not, and then you can move up and see how it works. Again, and I promise this is one of the last of these big diagrams. I have none more left. So at the bottom of it, we have our first patient 0, so the first infection where it happens. Immediately, it doesn't have a proxy. We're going to talk about the proxy in a bit. So it gets infected from the Cthulhu command and control server up here. It sends an acknowledgement packet saying, I have been hacked, or passes the flag in this case. And then at this point, the AI goes on the server, which is running on localhost, and downloads the quote-unquote virus. It's just a payload at the end of the day. One of the biggest things that the virus does, it installs a proxy. Again, the proxy that is included in Cthulhu is, you're going to see it, is a bit limited, but that's by design. So by design, this proxy is only able to send packets that are below 1024 bytes. But you can easily change that if you know anything about Python. Should be straightforward to do that. And the reason why I wanted a proxy is because one core difference in my polymorphic virus between all of the others is that whenever you hack into a machine and you infect a machine, the further attacks don't come from the command and control server. They come from the machine itself. So every single compromised node is now a proxy in your environment, which is why it's very efficient and can easily move within different layers of a network. Because once it infects a layer that is connected to 2 more networks, it can easily just proxy all the connections out. And it's also easier because you have one point of entrance. So the firewall, you need to breach the firewall only once, and all the subsequent communication doesn't go. You don't all of a sudden see all of your 500 nodes on your network communicating with this one host outside. You only see one communicating out. At that point, what it does, it just calls to the subnet and does the usual scanning. So target scanning, port scanning, generates a report, encrypts it with a uniquely generated key. The key, every single time we start Cthulhu, just completely changes. We generate a new one. It sends this reports back. The quote unquote, is not really artificial intelligence. The algorithm just reads this report back and chooses an exploit. Again, you can leverage MSF console. You can leverage Empire. You can leverage your own custom exploits if you put them in a specific directory, which is why you have a JSON file down here, which contains the list of all of the exploit you want to allow your virus to use. And this is very important because you have complete control of what your virus and your Cthulhu can and cannot do. So you can tell it exactly to only attack SMB using certain exploits, or you can just put stars everywhere and just let it go, just, hey me. Next thing it does, it chooses, of course, a payload. Again, it could be MS Venom for ease of use, or you can just write your own if you're a lead hacker. For both of them, what it does, it runs them through Veil, or again, MS Venom, or whatever you want, and it does a bit of code polymorphism to hide everything, and then it cross-compiles the static parts of the virus. So this is the code that is responsible for generating that virus that we downloaded initially on our targets that contains the proxy and the communication method and all the port scanning and target scanning. It can be, because it's written in Python, it can be compiled for virtually anything you really want to. And then you serve it via a simple HTTP server. So every single time you want to download it, just obligate from your victim, and you have a fresh compiled, completely changed version of this virus. And of course, what happens is then you use the exploit that you created to attack your patient number one. Once it's attacked, you repeat from the start. So you just download the virus from your local host and you keep going. Talking about behavioral analysis, and then we will have the demo, I promise. So behavioral analysis is different from signature-based or heuristic-based. So you're not really looking into what is the file that you downloaded, what are the strings containing the files that you downloaded, what are the libraries that this file calls whenever it gets executed, because all these traditional measures and signature-based kind of like methods work well, but not well when every single time you get attacked, you have a completely different payload, an exploit, and is in a different language. So strings are going to be different. The libraries called are going to be completely different. Even the logic is going to be different in the way it achieves the goal. So what we're looking at is network activity. So the idea behind this is to deploy sentinels, or as everyone else in the world calls them, honeypots, on your network to look at how the network works around. These honeypots will not only do a peek up of the systems that they can connect to make sure that there is no spike in connectivity, but they also spawn random ports that are known vulnerable ports to trick this virus to try and connect to them and hack them. And when they receive a connection, they read the package, they see if it is within their own internal libraries of malicious packages. And if so, they vote that that very specific system is compromised and is trying to attack all other systems. The way this works, and it works better, is if all these sentinels are deployed in your network using a Fibonacci sequence when it comes to hops. So when you measure the distance in a network, you measure it in hops. So how many links do I have to go through before I can actually connect to you? So from every single target, you want one sentinel to be at one hop distance, 2, 3, 5, 7, etc., etc. And the votes that they cast to the central command and control server for the defensive mechanism will be weighted based on the distance to the hop they're voting to the target that they're voting against. So the furthest away I am, the more my vote is going to count. Because if I'm very far away and I can already detect some malicious activity, it means that definitely something dodgy is going on that node. And now the demo, so you can see how this fails miserably. So what I have here is, on this virtual machine, I have victim number 2, victim number 1. This is Cthulhu, which is the code I'm going to release. So what we want to do is start Cthulhu. This file's here, so we're just going to run it. And what it does, it just generates the whole server and starts some connections. And then we just run the first infected virus. So what I've done here with starting Cthulhu, you can't really read, but first of all, let me see if I can make it a bit bigger, because it doesn't look like it. No. can't make it bigger, I'm sorry. I'll just read it out. So the first step it goes through, it initializes the server for the primer's delivery. So in this case, it just spins up a server and waits and is able to basically deliver all of the primers that we have encoded and created. Second of all, it just generates a random key for the tunnel. This way, every single communication that is sent back from any of the victims is going to be encrypted with a unique key. Then it writes the secret key to the header of the non-compiled version that will be later on compiled. And it starts the communication tunnel. It just waits for a connection to arrive. What we did later after that was running this, locally running a version of the virus. So that what this is doing is creating that first initial report. So I infected my machine, and my machine just went on and looked in the internal network to try and see which other machine it could communicate to and which ports were open. Created this list, I encrypted it, sent it over to my other program, which then received the communication from this internal node, decoded the communication, and then just said, I can see 3 targets, 56.3, 0.2, and 0.4. And for each of, every one of them went to my JSON file, and my JSON file right now only contains Samba exploits, and basically has started trying compiling different exploits for Samba, different payloads, creating all these machines, and using multi-threading, just attacking these systems. It didn't fail the demo for once, because here at the end, we can see that targets 1.4 and 0.3 have been both compromised. So we managed to successfully hack into these 2 targets and get the communications back. And now it's just going to stay there and listen. Of course, these 2 targets have downloaded their own version of the virus, but there are no more systems to infect because I only have 2 machines. So it's just going to wait there and see. I couldn't, because I only have my puny laptop, spin up more than 2 virtual machines. But if you clone your copy of Cthulhu, do a bit of configuration, you can spin up as many machines as you want. You can try this yourself, and you can see how fast it goes. So the concept, the key concept of this, and the reason why I infected my own machine as the victim 0, was because by infecting my machine as victim 0, I created a proxy on my local host. So all of these 2 attacks, to 0.2 and to 0.4 and 0.3, have been done using a proxy coming directly from my attacking machine, which doesn't really make sense. But if I had a 3rd virtual machine, I could have started the attack from there, and then all of the attacks would have been tunneled through that 3rd machine. I do not have a live running copy of the antivirus, but what I do have is a video I made for my dissertation, in which I was running the 1st edition of Chimera, and in which I also had the antivirus working. So what you see in the screen is this. Lower here is the command and control server for the defensive team. Up here we have Chimera, so the attacker. This is victim number 1. This is victim number 2. This is Sentinel number 1 and Sentinel number 2. And what happens very fast is that you can immediately see how fast the detection is when we're talking about behavioral analysis compared to the normal string-based and signature-based analysis. So these 2 machines, the 2 victims up there, were running a fully patched operating system with their own default antivirus running and their firewall on default settings. And none of these tools detected all these attacks that we're going through. Whilst the other antivirus, which is Bellerophon, immediately detected a very weird different connection in the network, and immediately contacted the central command and control server to block and firewall off these 2 machines. Why do I do this? Well, this research, you need to bear in mind, wasn't targeted to normal enterprise networks or anything like that. It was targeted specifically to systems that were in proximity of safety critical systems. And these systems don't have much RAM, CPU, so they can barely run what they need to run, let alone an antivirus. And they heavily depend on a lot of dependencies and a lot of systems on their own network. So you can't just bring one of the nodes offline because you know it's infected, because that will actually probably make your whole, nuclear power plant to go boom, and you don't want that. So this first initial version, instead of taking any proactive action on the network, was just notifying the sysadmin, which then as a human could go and say, okay, there's not an indispensable node, I will just shut it down. Or they could go, okay, no, I can't actually shut it down. Having it infected with a virus is actually okay and way better than having my system go offline and not being able to control temperatures and that kind of stuff. But the principle of using honeypots to look at your network could be automated, and you could have any kind of behavior triggered for whenever you detect that something is actually going wrong. So you could quarantine a certain system, you could power off the system and revert it back to any known good state. You could do any number of action that you would like to code. The whole takeaway here is that looking at behavior when you have a threat that is constantly changing on your own network is much easier than trying to understand the trend in strings and behavior that a singular file has, because we as attacker can easily change that very, very fast. What I did in the last iteration of Chimera, and I think is the natural progression of this kind of attacking pattern, is by using AI. Well, we've been to the machine learning and AI talk this morning, and probably I'm not using the word AI in the correct term there. But what I have there is, if anyone has done any machine learning course or class, is an example of Q-learning. So Q-learning is normally used to teach AIs the best way of getting out of a maze. So you have a certain set amount of possibilities for every step that you take, and you have a starting position and an end position. If your starting position is, I am out of a system, and your end position is, I have compromised the system, every single layer that you have there could be the choice of language, the choice of exploit, the choice of payloads. Then you could have another one, which is the choice of evasion algorithm. So it could be your shikata, it could be your just not slides, it could be different things. And then you could have how many times you've run these different things. So if you create a Q-learning cube for each of these decisions, and you measure the success of each and every campaign that you run, you will end up at the end of the day with a fairly accurate map of what is statistically the best way of compromising a certain subnet. And this is based on the assumption that normally when you think about big companies, when you think about every big system, they tend to put similar systems in the same subnet. So whenever you land on the same subnet, they usually is the subnet that is for all the developers. So they all have these Windows 7 machines. They all have these programs installed. Then you go on the prod network. They're mainly Linux machines with mainly this configuration. You go on the HR network. They have different configurations. So if you create a Q-learning map for each and every one of these different networks, at the end of the day, you will have a very accurate map on what your vulnerabilities are. And because you're leveraging a tool that constantly changes his aspect, his behavior, you're going to have a very accurate representation of what that network looks like vulnerability wise. The takeaways from this is that as a community, we need to move fast. I started this research in 2017, yes. The beginning of 2017, across 2018. And even then, doing some research, reading some papers, I clearly saw that the trend in generating viruses is to try and make them clever, intelligent, use machine learning, use the power of the clouds to compute passwords, to steal Kerberos tokens, to do pass the hash attacks. They wanted to automate all these different steps. The viruses that actually hacked into a lot of UK e-commerce, and they were discovered a few weeks ago by researchers. This virus they estimate that they started writing this virus in 2016, which is a proof that in a couple of years, these kind of attacks will be perfected, will be used in the wild, and will be just normal. I do not claim to be an expert in this by any stretch of imagination. When I started this research, I knew absolutely nothing about writing a virus or how a virus worked. And in the 9 months of my research, I just went to conferences, talked to people who do this, and they're way more clever than me and do this for a living. And I asked them what the most common techniques are. So I really wanted to release something to the wider community, because there are a lot of smart people in this room that could read my code, cry a bit because it's so awful, and then make it way, way better and take out something that is actually useful for the community and for the safety of the rest of the web. And we need to move fast, because these things are already developed by people that have bad intentions. We need to stay up to date. Think about Kerberos enumeration. Kerberos thing is almost a given. So if you're doing a red teaming exercise and you land on a system that is using Kerberos, first thing that you try to do is Kerberosing, or stealing some of the tokens and passing the hash, or doing some of these attacks. And if you do this like 10 times, you're going to see that a lot of these steps can be automated, and they could be done at the level of Chimera. If any one of you know the absolutely great tool that is Bloodhound, that can generate a map of how these things actually work, you can automate these tools in a more efficient way. Another thing is living off the land, which is the new trend in attacks. And by using living off the land techniques, you can exploit the configuration that your victim has already on their computers without having to import your own tools on the software. Finally, experiment. Try your hand at this. Read about it. Create publications. Create pull requests, merge requests. Talk about it, and let's try and be ready as a community. What I'm trying to do with all this is to try and get this research published at some point in the future. Speak at conferences, because I like doing this, although I'm probably not that good at it. And enrich the POC. I do this on my free time, on top of trying to prepare for OSCP. So I don't know how proficient I will be in the next month, but think about using Empire, thinking about using custom rules. All these different points are stuff that I really want to implement in Cthulhu, because I've implemented in Chimera and they worked very well. And they can all be implemented very, very easily, because, as I said, it's very modular. So you can just scrap what I've written, write your own stuff, and it will still work, the whole package together. And with this, it concludes my talk. Thanks a lot for listening. I will publish the link to my GitHub, both on my website and on my Twitter accounts, after this whole thing is finished, possibly before I get drunk at the after party. But if you have any questions, just contact me on Twitter or on my website. I'm going to be around. And if you have any question, I'm happy to answer them.
I have a question. So, where do you see Behavioural phone going? Because you've got these honeypots.
Yes.
Okay. So if you set it as a honeypot, it's just going to tell you, hey, there's something going on in our network.
Yes.
But you also envision it being like an antivirus, like an endpoint antivirus type thing?
Yes, absolutely.
Okay.
So imagine having a big corporate network with, you have like 500 or even thousands of machines, right? Spinning up a single, very small honeypot here and there in your network costs you absolutely nothing in terms of resources or time. And if you get the data from this, innocent honeypots around, it gives you a more proactive vision of. So when I was, for example, seeing the attack propagating through different layers of the network, all the traditional intrusion detection systems deal with this kind of attacks as they come in. So if it's a proactive firewall, it will deal with stuff when it starts hitting the firewall. If it's an antivirus, it will start caring about the files when you start running them, right? If you're looking at the behavior of the machines around you, you can understand which one are compromised and you shouldn't trust. And then it's up to you what you want to do with it. As we said, you can quarantine them, you can.
Yeah. And how do you know that the honeypot's been compromised, is going to be sound enough to report that is compromised.
So, the one cool thing that I did, and it was inspired by a course that we did at Glasgow University, which is a safety critical system, is something that is done on planes nowadays. So airplanes have not only one computer on board, they have various computers on board, and they cyclically, every single computer votes on the sanity of all the other computers.
Okay.
So every honeypot doesn't only look at what they're trying to protect, but they also vote on each other's sanity and make sure that they're not compromised or their communication are still up and running. So it wasn't my idea. I took it from planes. Anyone else? Yeah.
In regards to your honeypot, you didn't particularly go into, is there a lot of modularity there? Are you able to import, say, like create your plugins?
So I'm not releasing right now, but I will in the future, a POC for the honeypots, because the way I coded them was probably like 50 lines of bash. So all you want to do is you have a list of ports that you want to spin up, maybe a list of banners that you want to fake to have. And what you do, you just cycle through them, spin up the port with the banner behind it, and then you just read from the socket, and then you have an if condition, and you just notify. And with the sanity is literally you have a list of all the other honeypots. You periodically ping each other, make sure that you pass a secret, and that's how you vote on your sanity. So it was actually very, very easy. It was scarily easy how solutions that cost a lot of money were not detecting these kind of attacks. But this 50 lines of bash that a first year students could have written was actually detecting them immediately. Anyone else? No? Okay. Thanks very much for listening to me.